So I thought I'd give a little bit of motivation for equivalence relations and equivalence classes. This is sort of the last line of the section 8.3, and it sort of says it all. If your goal is to build up common mathematical objects, including number sets like the natural numbers, the rational numbers, the real numbers, and so on, then you might want to do that using your mathematical foundations, your logic and set theory. So using equivalence relations, you can define the rational number set from Cartesian products of integers, which we've already talked about. So let's go through the construction of the rational numbers as equivalence classes. So first, consider the set of ordered pairs of integers, the second of which is not, we don't write it like that, is not 0. So take the set of integers and make a Cartesian product with the non-zero integers. Okay, so we consider this set, and then we define what turns out to be an equivalence relation on that set. So we define the relation R in the following way. So the relation R is on this set, on this Cartesian product, and here's its definition. If you have a pair of integers, a second one non-zero, we're going to call it related to another pair of integers, the second coordinate of which is not 0, to mean the following. A times D is equal to B times C. So this is a condition for two ordered pairs of integers to be related to each other under this relation. So the first thing to prove is that R is an equivalence relation. Well, we know that that has 3 parts. We would need to show that R is reflexive, symmetric, and transitive. The book sketches out transitivity. I'll do symmetry here, and you can do reflexivity on your own. So I'll just prove this one claim. R is symmetric, partly because that's a good exercise anyway, to remind you how to prove that a relation is symmetric. So off to the side, I'll remind you what a relation being symmetric means. It means for all x and y in a set A, if x is related to y, then y is related to x. It's a conditional, all right? So the elements of our set are ordered pairs. Be careful with that. So I'm gonna set up the front end of this conditional carefully. So I'm gonna suppose that I have 2 elements in the set, and we're gonna suppose that the first element is related to the second element. Well, let me spell out what that means. The relation has meaning. AB related to CD means this equation here. Then I know that that means AD equals BC. Now watch this. I know equality goes both ways, so BC equals AD. Okay. So let me come up here to the definition to help me see what's happening here. If I have one element related to another, it needs to satisfy the equation like this. All right, so if I come back down to my equation and rewrite it so this is explicitly clear. So look what I have here. I have that CD is taking the same place in this equation as AB was up there, and then of course the BA is taking the same position that D and C did in this equation. So that's just like a long drawn out way of saying that I've concluded that CD is related to AB. Okay, so you can show, as I mentioned before, that this relation on the ordered pairs of integers is an equivalence relation. So you can set up the equivalence classes. So Q is defined to be the set of equivalence classes on this set defined by the relation R. And this is really weird because, just think about it for a second, an equivalence class is a subset of this Cartesian product. And we're saying then that Q is acting like a set of subsets of this Cartesian product, which isn't what we think of it at all, right? We think of Q as a set of numbers, but this is formally how those numbers are actually constructed. So for example, like pick your favorite number, let's say, 5 over 7, that's a good rational number, right? So 5 over 7, a rational number as we think of it, is technically the equivalence class of, well, I could even say it like -10, -14. This ordered pair is equivalent, well, in particular to 5, 7. It would satisfy the equation. Go ahead and verify it. And it's equivalent to any other pair of integers, the second of which not being 0, that basically make a ratio of 5 to 7. So this right here, this equivalence class of ordered pairs of integers, is the number 5 sevens, or that's how the number 5 sevens is defined formally. Okay, so I just maybe make one more comment. You can define formally, using logic and set theory, the rational numbers in this manner. And from there, you might want to define the real numbers. And it's a lot trickier once you get to that stage. There are two common ways to construct the real numbers from the rational numbers using set theory and logic. The first is Dedekind cuts. So you can define the real numbers to be certain subsets of rational numbers. The other one is to define the real numbers to be equivalence classes of Cauchy sequences of rational numbers. So there's the term equivalence classes coming in yet again. But anyway, when all is said and done, the importance of equivalence classes is apparent in this construction here. And you will encounter equivalence classes in pretty much any other area of math.